Hello everyone, my name is Khaled Serag. Today I'll be presenting our paper exposing new vulnerabilities of the air handling mechanism in CAN. CAN has established itself as the main internal communication medium for vehicles. While initially its main goal was to reduce the amount of wiring required for communication on a vehicle, features such as decentralization, noise resistance, air handling, and fault confinement all made CAN the go-to choice for automotive manufacturers. Thanks to CAN, vehicles are now called computers on wheels. However, recent works have shown that one of CAN's most desirable features, namely its air handling and fault confinement mechanism, makes it vulnerable. In light of this advancement, we decided to further analyze CAN's air handling and fault confinement mechanism to detect possible vulnerabilities. To start with a background, CAN is a broadcast-based bus that uses differential voltage signaling between two wires to communicate messages. A 0 is represented as a dominant signal, and a 1 is represented as a recessive signal. Dominant signals trump recessive signals, which means zeros have a higher priority than ones. At the beginning of every CAN frame, there's an arbitration field containing the message ID and the RTR bit. A CAN message ID with more leading zeros will have a higher priority than an ID with more leading ones. CAN message IDs do not convey the sender or the receiver of the message, but rather its meaning. As a result, even though any node on the bus can listen to all messages from all other nodes, an observer cannot know by listening alone who the sender or the receiver of the message is. One of the main reasons for CAN adoption is its air handling and fault confinement mechanism. Since CAN was intended to operate for extended periods with no external supervision, it was necessary for the network to detect, contain, and resolve errors on its own. This is done by defining a set of errors to be watched for by every node on the bus. Additionally, each node maintains two counters, a transmit error counter TEC and a receive error counter RAC, to keep track of the errors encountered during transmission and reception, respectively. CAN also introduces the concept of error states. By default, nodes operate in the error active state. After a certain amount of transmit or receive errors, the node moves itself into the error passive state, where stricter transmission and error signaling rules are applied. If transmit errors persist, the node moves itself into the bus off state, where it disconnects itself from the bus. Recent works have shown that an attacker can get access to the CAN bus by compromising certain ECUs, such as the telematics unit. Since CAN was not designed with security in mind, an attacker can use this access to launch further attacks against safety-critical functions, such as the brakes. Of specific importance are attacks that directly target CAN's air handling and fault confinement mechanism. Specifically, recent works have shown that it's quite straightforward for an attacker to cause deliberate collisions on the CAN bus by sending a message with the same ID as another message on the bus simultaneously, but with a different content. This allows the attacker to dictate the victim's error state. This ability is extremely dangerous, since CAN nodes were intended to only operate in the default error active state, and to never leave it except under extreme error conditions. We argue that the impacts of operating outside of the error active state are hugely understudied, and that the vulnerabilities lying outside of it remain uncovered. We introduced CAN Operation Explorer, or CANOX. CANOX explores the impact of operating outside of the error active state to identify possible vulnerabilities. The way CANOX works is by placing a fully programmable node named the node under test, or NUT, in a controlled test environment. NUT is then operated in different scenarios where it logs its behavioral metrics throughout the experiment. We consult the standard to identify the scenarios in which we expect the error passive and error active behaviors to differ. We do the same to identify the best behavioral metrics. Within each scenario, NUT is operated once in the error active state and once in the error passive state. Further, within each scenario, we vary the bus load and traffic priority. If NUT's logs show significant behavioral differences between states, the log analyzer flags the scenario as possibly vulnerable. Using CANOX, we were able to unveil three important vulnerabilities. The first vulnerability is what we call the passive error regeneration vulnerability. Since passive error frames are composed solely of recessive bits, they have a lower priority than any other frame on the bus. meaning they can be interrupted by any other frame on the bus. It turns out that if another frame interrupts a passive error frame in its delimiter portion, the sender of the error frame considers that as yet another error, and it tries to signal this new error by sending yet another passive error frame, which in turn could face the same interruption. An attacker might be able to exploit this vulnerability to launch what we call the single frame bus off attack, in which an attacker could push a victim to the bus off state by attacking a single message. The way an attacker could do that is by first starting a simultaneous transmission with one of the victim's messages, leading to a collision on both the attacker and the victim's side, who will both try to signal this error by sending an active error frame. Because of the automatic retransmission feature enabled by default on all controllers, both the victim and the attacker will attempt to retransmit their message right after the conclusion of the error frame, leading to another simultaneous transmission and another collision. This self-destructive mechanism will repeat 16 times, at the end of which the victim will fall into the error passive state and try to signal the error using a passive error frame. Here, the attacker sends 15 back-to-back clutter messages, interrupting all the victim's passive error frames. This will cause the victim's TEC counter to rapidly increase until it falls into the bus off state. The same mechanism could be used to set the victim's TEC to a specific value within the passive error state by controlling the number of clutter messages. The second vulnerability is what we call the Deterministic Recovery Behavior vulnerability. We noticed that when we push a victim to the bus off state by attacking one of its messages, the victim attempts to send the same message at the moment it recovers back into the error active state. The problem with such a deterministic behavior is that if the attacker is able to estimate the recovery time, the attacker will be able to re-attack the same message at recovery since it knows its ID and content. This allows for what we call the persistent bus off attack, in which an attacker keeps the victim ECU in a perpetual bus off state, constituting a persistent denial of service attack. The third and last vulnerability is what we call the error state outspokenness vulnerability. We noticed that the way error active nodes retransmit their failed messages or send successive messages differs from the way error passive nodes do. An attacker may be able to detect the error state of a message sender by passively observing such behavior, or actively by causing a collision and watching how the victim retransmits this message. This could be extended further to map the entire network. The attacker may be able to map all the messages that emanate from a single ECU by attacking one message, sending its source ECU to the error passive state, then observing what messages manifest an error passive behavior. Although each of the discovered vulnerabilities could be used separately, we choose to combine them into a single end-to-end multi-stage attack to show their gravity. We call this the scan and strike attack or the STS attack. In this attack, remote attacker with no previous knowledge of the network internals observes messages on the CAN bus. Next, the attacker uses the error state outspokenness vulnerability to map the internal network, then uses the same vulnerability to identify a safety-critical ECU such as the electronic brake control module. The attacker then uses the passive error regeneration vulnerability to push the ECU to the bus off state and observe how it recovers. Once the attacker learns the ECU's recovery behavior, they use the Deterministic Recovery Behavior vulnerability to persistently keep the ECU in the bus off state. This way, a remote attacker with no prior knowledge of the vehicle's internals can identify a safety-critical ECU and permanently shut it down. For validation, we evaluated the STS attack on both a testbed and a real vehicle. On the testbed, we connected 4 ECUs, each transmitting 4 periodic message IDs. We were able to map all the IDs to their source ECUs with 100% accuracy. To evaluate the persistence of our bus-off attack, we define a metric called the suppression rate, which represents the amount of time the victim is kept in the bus-off state as a percentage of the total experiment time. As can be seen in the table, we were able to achieve a suppression rate approaching 100% on all ECUs. On the test vehicle, we were able to map all the messages on the network with 100% accuracy, identify all ECU functions, and achieve a suppression rate ranging between 83 and 97.5%. Finally, We show a demo of how a persistent bus-off attack could take place. Here, we have a victim ECU sending two periodic messages with different IDs, ID1 and ID2. We will suppress this ECU by attacking ID1 and preventing all of its recovery attempts. Now we upload the attack code. As can be seen, on the ID1 window, we can only see the attack messages. In the ID2 window, we can see that all messages have stopped. To ensure responsible disclosure, we reported the vulnerabilities to the Robert Bosch Security Incident Response Team, the Cybersecurity and Infrastructure Security Agency, who created an open case to discuss the vulnerabilities, and to the Society of Automotive Engineers, who acknowledged their contributions and submitted the vulnerabilities to a committee for review and consideration in the next revision of the standard. On our part, knowing that a standard revision might take a long time, we also proposed some mitigations to each of the discovered vulnerabilities, which could be implemented immediately. In conclusion, it turns out that the extent towards which CAN's air handling mechanism is vulnerable is surprisingly much greater than previously thought. We introduced CANOX, a protocol testing tool to examine CAN's air handling and fault confinement mechanism. To the best of our knowledge, this is the first attempt at designing such a tool. Through CANOX, we unveiled three major undiscovered vulnerabilities, each of which could be used separately. We chose to combine all three vulnerabilities into a single end-to-end multi-stage attack to emphasize their significance. Finally, we validated the practicality of the attack by evaluating it on both a testbed and a real vehicle, achieving very high rates of success for all phases of the attack. Thank you.